What if the key to unlocking the next leap in quantum computing isn't in futuristic labs, but hidden in the tiniest interactions of electrons within a crystal? A groundbreaking discovery from a Japanese research team might just change the game. Imagine electrons, those tiny particles we've all heard about, acting like they've gained weight, not through calories, but through quantum magic. This phenomenon, known as heavy fermions, could be the secret sauce for building quantum computers that defy today's limits. But here's where it gets controversial. These electrons aren't just heavy. They're dancing in a synchronized quantum entanglement, and their movements are governed by the smallest unit of time in physics, the Planckian time. Could this be the missing link we've been searching for in quantum tech? Let's dive in. Heavy fermions aren't your average electrons. When they interact with localized magnetic electrons in certain materials, they behave as if their mass has skyrocketed. This isn't just a quirky side effect. It's a gateway to strange properties like unconventional superconductivity, a hot topic in condensed matter physics. The star of this study? A material called cerium rhodium tin, CeRhSn, which sports a unique quasi-kagome lattice. Think of this structure as a geometric puzzle that creates frustration among electrons, forcing them into unexpected behaviors. But this is the part most people miss. The team found that CeRhSn's heavy electrons don't just act strangely. They stick around in this quantum state up to near room temperature, which is a big deal. Why? Because most quantum experiments require freezing temperatures, but this material might work at conditions we can actually use. How did they crack this? By peering into CeRhSn's reflectance spectra, the researchers spotted something rare: non-Fermi liquid behavior persisting at higher temps than ever before. To put this in perspective, imagine a dance where the rhythm breaks all the rules you thought you knew. The electrons here follow a single mathematical function, hinting they're deeply entangled. Dr. Shin-ichi, leading the charge, explains this isn't just theory anymore. We've directly observed that these heavy fermions are quantum entangled, and their timing is dictated by the Planckian limit. It's a huge step toward untangling how entanglement and heavy fermions work hand in hand. So, what does this mean for quantum computing? Entanglement is the lifeblood of quantum systems, allowing qubits to share states instantaneously. If materials like CeRhSn can host this entanglement at manageable temps, they could become the foundation for new quantum architectures. The Planckian time limit acts like a speedometer for these quantum processes, telling engineers how fast they can push these systems before chaos takes over. But here's the twist. Some experts argue whether this discovery will translate into real-world applications. After all, lab breakthroughs don't always survive the leap to industry. What's your take? Is this the dawn of a quantum revolution, or just a clever trick of physics? Share your thoughts below. The team's findings, published in NPJ Quantum Materials, paint a vivid picture of electrons defying expectations. Figure 1 shows these heavy electrons entangled in CeRhSn, while Figure 2 reveals their dance of atomic structure and quantum timing. As the field races forward, one thing is clear: the line between science fiction and reality is blurring faster than ever. Will heavy fermions lead us to quantum utopia, or will they hit a wall we can't see? Only time, and maybe Planckian time, will tell.